had talked about two-level logic optimization. Today we will be extending our discussion and we will be talking about multi-level logic minimization or optimization. We had mentioned that there are many circuits for which multi-level logic optimization proves greatly beneficial as compared to two-level logic. We will start by giving an example of such a circuit for which multi-level minimization helps greatly. Okay. There are a few things you need to look at, that when you talk about multi-level realization, it is not only just the number of levels we talk about. There is also another thing which need to be looked at, that is the number of inputs to the gates which are required. As I mentioned, that as you have a gate with high number of inputs, gates become slow. Just a simple example, suppose you have a 9 input OR gate. Okay. Now this 9 input OR gate you can implement in two-level realization like this using NOR and NAND. Now apparently you can say that here there is only one level and here there are two levels, but in practice this gate is much slower because of this high fan-in, because of the high capacitive of the high impedance the capacitive load has to face, as I had mentioned in the last class. So particularly for high fan-in gates, it is beneficial to break that gate up into smaller gates into multi-level logic. So this is one situation where multi-level logic realization makes sense. Break up a gate with a large number of inputs into multiple levels of smaller gates, your speed will improve. Well, another case is, as I said, that for some kind of logic multi-level minimization may prove to be expensive. So let us take one example of that category. That example is the XOR function. An XOR function, if you recall, it is a circuit where let us just take an 8 input function. For an 8 input function, say I have an XOR gate. I have 8 inputs. Now in 8 input function, I can suppose I want to realize this in a two-level logic implementation. Now in a two-level logic implementation, you think of an XOR gate. What is the kind of requirement you have? So an XOR gate is essentially a parity detector, right? So just let me tell you, I am drawing this big XOR gate. If there are 8 inputs, the output will be 1 if odd number of inputs are 1. Odd number of input means 1 of the input is 1, 3 of the inputs are 1, 5 of the inputs are 1, 7 of the inputs are 1. Okay. Now actually how many such combinations are there? The number of combinations will be this out of 8. So there how many ways I can have one input to be made 1, 3 inputs, 5 and 7. This makes 128. And another thing is that one characteristic of this XOR gate is that the true minterms, for an XOR gate, the true minterms have a distance of more than 1, which means they are never connected by a single edge in the cube representation. If they were connected by an edge, they could have been combined in a cube. But for example, for a 2 input function, say if we have A XOR B, the function says A naught B or A B naught. They cannot be combined. Similarly for 3 input, 4 input XOR, they cannot be combined. So whatever number you have obtained here, that will give you the number of NAND gates. And since there are 8 inputs, each of these NAND gates will be having 8 inputs. So, you need, this number comes to 128, you need 128 8 input NAND gates. So, in the first level you will be having so many NAND gates, and in the second level you will be having one big NAND gate feeding all these, 128 input NAND gate. So, you try to understand that this 8 input XOR I can very easily implement in a 2 level implementation, 2 level realization, but I am getting, or means I am requiring 129 gates, all of them are of very big sizes, say the one of them is of extremely big size, 128 input. So, this is possibly not practical. Now, let us try to think of the other way around. So, how do we do it? Can we break this up into multiple levels and do it? See, this 8 input XOR we can also implement like this by using smaller 2 input XOR gates. Suppose we have something like this, we use cascade of XOR gates like this. And you please note, all are 2 input XOR gates. So, we need 7 2 input XOR gates, and each 2 input XOR gate can be implemented like this. This. So, effectively each NAND gate, each XOR gate is equivalent to 3 levels of NAND, and there are 3 levels of XOR. So, we have 9 NAND levels in total. But the advantage we gain is that we need only 4 into 7, 28 2 input NAND gates. This is the big advantage we get. So, we require 28 2 input NAND gates. Number of levels have increased somewhat, but as I have again mentioned, the delay of this alternate realization will be much less as compared to this simplistic realization. Okay. So, this particular example tells you or shows you that there are some examples of circuits for which 2 level realizations are not feasible. We must go for multi-level realizations. And for multi-level optimization, there are a number of methods which have been reported. Now, broadly, these methods can be classified into local and global. Local means that you look at one of the equations or one of the outputs at a time. You try to do some kind of local optimization. So, you look into a netlist, you look into a circuit, you look into a small part of it and try to do some optimization there. Global optimization means you look at all the functions at the same time and try to do some transformations on all of them, so that you get some optimization. Now, since you are looking at the whole problem at the same time, this is called global. In contrast, the earlier method is called local. So, let me try to give you some idea that how these local and global transformations work. So, as you can see, it is written here, local transformations, local optimizations are based on some kind of rule based transformations. Let us see what kind of rules. So, the objective of these rule based transformations are, of course, same: reduce area, delay or power. They are again mutually conflicting. So, in these methods, the main problem is to develop a good set of rules, because you have a set of rules which you repeatedly apply to a netlist in order to improve upon it. You have a given netlist, you have a set of rules, you see that whether you can apply a particular rule to a part of the netlist. If you can, you get an optimization out there. So, you will have to enumerate as a designer the list of all such rules you need to apply and check for this kind of local optimization on the circuit. And again, these rules should be comprehensive enough. Okay. Now, the basic idea is what I have just mentioned, that you apply one of the transformations to a given netlist which reduces the cost of the implementation, and you go on iterate. This is a greedy approach. You iterate and continue applying transformations as long as you get better and better solutions. So, this is a purely greedy approach. It is applied on a given netlist based on a set of rules. Now, the kind of rules that are used or applied are fairly simple. So, the first set of rules are like this. These are called simple AND OR transformations. I have shown some of these rules. Many of them are based on simple, you can say, the simple identities of Boolean algebra, A and 1 equal to A or 1 equal to 1, this kind of things. So, if in a circuit you encounter, for example, this, if you encounter two NOT gates in cascade, obviously you will replace everything by a single wire. Okay. So, XOR of some input set of inputs and B is the same as a single XOR gate with all of them as inputs. So, if this means if you have XOR of some inputs and another XOR of some other input, then you replace it by a single XOR gate with all the inputs. So, this kind of rules can be there, many of them. These are very simple rules, fairly simple rules. You just apply these rules to them one by one. Now, another thing is that most of the practical implementations or realizations are based on NAND or NOR logic. Now, this requirement comes out from the ultimate, you can say, the target you are trying to implement on, typically CMOS, and you know CMOS can realize only negative gates, NAND, NOR, this kind of things. So, in general, after these transformations you will be getting a netlist which will contain AND and OR. So, after that what you will be doing after this AND OR transformations, you will be translating this AND and OR gates to NAND or NOR form. Now, you know that how a NAND gate can be how a AND gate can be converted to a NAND gate, NAND followed by a NOT. Okay. Similarly, OR to NAND, this you know. So, after doing this transformation, you will be getting say, I am giving an example. Suppose you had a circuit like this, an AND followed by a OR. Okay. Now, after doing this transformation, what you get is this AND will be replaced by NAND followed by NOT, and OR will be replaced by NOT, NOT, NAND, NOT, this kind of thing. So, you see that after you do this kind of translation, these kind of chains of NOT gates are very common. You can combine these two NOT gates into, and you can make it a single one. You can replace them by a single wire. So, after these transformations, a number of additional optimizations will come up which you can apply, but here the advantage is that you need to concentrate only on NAND or NOR. Okay. So, there are a second set of transformations you need to apply here. These are called NAND or NOR transformations. Now, here after this is done, you can very well assume that all gates are of the same type. Okay. Typically, we use NAND more often than we use NOR. So, since all gates are of type NAND, and which is one of the basic gates, you do not require any specific technology mapping, because NAND is always a part of any library. and now we have a set of rules which are framed based on Nand or NOR networks. Like you have an example out here. This example means, you see, you just try to understand what it means. Nand of A and B, which means you have Nand of A and B, not of that, Nand of that and C. There is another Nand with C. So what this rule says, that if you see that you have a netlist like this, a subgraph like this entire thing is equivalent to a 3 input NAND. So you can replace it by a 3 input NAND. Similarly, if you have NAND of ABC, NAND of ABC bar, NAND of that C goes, you simply have a 2 input NAND A and B. So here I have only shown a couple of rules, but there will be a big set of such rules which you can apply to this NAND level netlist and you can carry out optimization. But you see that this now becomes a search problem. The given netlist which you have, that is like a big graph, and the rules that you can potentially apply on them to carry out optimization, they are like small subgraphs. Now you will have to search the netlist for presence of those subgraphs, and if you see that one of those subgraphs are present, you can apply that rule to carry out that optimization. And more you do the optimization, your circuit will become smaller and faster possibly. So, and I said that this is a greedy approach. Here you look at some rules and you look at some parts of the circuit where that rule can be applied, and you straight away apply that. Okay. But here you are not looking at the total picture at a time, looking at say all the functions, looking at how to make transformation to the circuit, so that you can say globally we can have some optimization. We are not looking at that. We are looking at some local benefits by making some transformations here and there. So talking about global optimization, the technique we mentioned was used in a package called Socrates. This uses a method called weak division. See, idea is very simple. This is a very well known method which has been used for a long time by the compiler writers. Basically, you try to identify the common sub expressions and you try to divide them out. See, common sub expression means if you have, say, if you have a function AB plus AC, well, which you can write as A into B plus C, and you have another function, say only B or C, then you can see that this is a common sub expression, and instead of evaluating it twice, why don't you evaluate it only once? This F1, instead of writing A into B plus C, I can simply write A into F2. So I can save one OR gate, right? So the idea is this, that if you can identify the common sub expression, you evaluate it only once using gates, and that you use it in the other place. So you can save on the hardware. Now in this approach, you use the following iterative steps. The idea is again simple. You find out all possible sub expressions which are common to 2 or more Boolean equations. Now after that you try to evaluate. Suppose you see that there are 4 possible sub expressions. Now you try to find out which one of them is better. There must be a way to evaluate. Now the one which is best you find, you use that for factoring the equations, and you go on repeating this. So select a sub expression to divide based on the goodness measure. I will show how we do that. Then you actually divide the functions. Now see, dividing up into sub expression and using it, this is something like division. That is why the term weak division is used. Now, I am explaining these steps with an example. Suppose I have a problem like this. There are two equations or two expressions to be solved. Actually, this corresponds to a circuit comprising of two outputs, F1 and F2. This A, B, C, D, E, F, G are the inputs, GH. Now our measure of goodness is simply to count the number of literals. This is a fairly, you can say, accurate approach, and many methods simply count the number of literals in order to estimate the cost of implementation. Now, in the original one, how many literals are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So, in the initial problem, number of literals was 18. But if you look at these expressions now and you try to find out what are the common sub expressions which exist in any one or more than one. First you see BC. BC is present here, here and here. AB. AB is present here and here. A or D. Well, A or D you can have from here by factoring, by taking BC common, A or D, that is all. BG, BG is here and BG is here. Now, for each of these literals you estimate that if I use this factorization, that how many literals I am saving. So, I am not showing the detailed step, but actually what we will do is that suppose you select for example AB. AB is the sub expression you select. So, you actually generate AB from some other, AB is here, AB is here. Suppose you write say U equal to AB and U you use here as well as here, and you count how many literals you are saving in the process. Okay. So, this process you repeat for all the possible sub expressions. You find that for this particular example BC gives you the best benefit. So, you select the sub expression BC. So, after the first iteration you modify the equations by replacing BC with some variable U, and wherever BC is there you replace it by U, and here also I am factoring it at the same time for the next step U. Okay. So, this is the new equation. Now, here you find that the number of literals is 14. So, we get a saving of 4. Okay. So, you go on repeating this. So, you have this with you, you have this is now the result at the end of iteration 1. Now, you check the sub expressions. Now, BG gives you the best benefit, BG. So, the next iteration you select BG. BG is here as well as here. So, define another variable called V, it comes V here. So, now the literals becomes 12. After this you find that there is no other common sub expression you can find. So, you stop out here. So, after doing this factoring and this division, apparent division, you get a modified specification, you can say, where the common sub expressions are not there, and wherever the common sub expressions were there, you had utilized them by division and you have reduced the number of literals out there. So, you had obtained some implementation which will be more efficient in the process. Now, the problem with this kind of an approach is that every time you are trying to go from a given solution to a better solution. So, essentially this is a greedy algorithm. Every time you are selecting the best approach. Okay. So, I am again repeating, any algorithm which always tries to go for the best alternative in the present scenario has a great chance of getting stuck into a local minima. It may miss out the globally best solution, it can get stuck into a local solution which may be far off from the best solution. So, this is a greedy algorithm, it can get stuck in a local minima, and there wherever or means whichever method has a chance of getting stuck in a local minima, somehow we give a jerk or some kind of a randomness to come out of the local minima. So, in terms of the contour of the solution space like this, if it is greedy, you will always go down, 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 you will get stuck out here. But from here, if you give a jerk like this somehow, maybe maybe from here you can start exploring another part of the solution space and you can get to another solution which is better, lower cost. Okay. And another thing is that generation of all candidate expressions is expensive. I have taken a very small example, but imagine if you have a very large number of equations with very large number of variables, generating all possible sub expressions which are common, that itself is an expensive process. Okay. So, some kind of heuristic must be used. Now, in fact, there are many multi-level optimization packages that have been reported and are used, and one of the methods I am mentioning very briefly about is one of the more successful and the most popularly used method. This is called MIS, Multi-Level Logic Interactive Synthesis. Now, this MIS also uses factoring of equation just like that weak division we just mentioned. And one thing out here is that this MIS specifically targets CMOS gate as the target technology. Okay. Target technology CMOS means that whatever equation I write, it is a negative equation, because I am showing you why. Let us take this example. This is a 3 input NOR gate. Now, in CMOS, a 3 input NOR gate will look like this. These are the 3 PMOS transistors and the 3 NMOS transistors are in parallel out here. So, we have A out here, B out here, C out here, A, B, C, and this is the output. And one characteristic of the CMOS gate implementation is that it always implements a negative logic. That means F equal to A or B or C not, or F not equal to A or B or C, whatever you say. Similarly, if you have something like this A or B and D or E or F H, this also you can implement very easily. So, you will be having a pull up network and pull down network. Say I am showing this A or B. So, I am first drawing the pull down network. There are 3 parts which are in series, and first A or B, A, B, and D or E or F, D, E, F, H. This is the pull down network. Similarly, pull up network will be the complement of this. So, it will be parallel combination of AB, these will be PMOS A and B, then there will be another DEF, another part, 3 transistors in series, this will be D, E and F, and another part only H. So, this will be connected to the pull up network. This also will implement a negative gate. So, when I say that the target technology is CMOS, it means we are trying to go for a solution like this. Now you see in this one the number of literals were 1, 2, 3, 4, 5 and 6. In terms of the CMOS realization, there are 6 transistors in the pull down, 6 transistors in the pull up. So if there are n literals, in terms of CMOS implementation we can very easily compute the cost. There will be 2n transistors. This is why number of literals is used sometimes to estimate the cost of a solution. Okay. So MIS specifically targets CMOS gates, and for that purpose it uses the number of literals as a measure of computing the cost. So basic concept is, well, at this level it is similar to Socrates. It uses algebraic factorization to identify common subexpression, but it tries to avoid exponential search by using some heuristics. And for local optimization, it identifies 2-level subcircuits and minimizes them using espresso. So from the bigger circuit, it also identifies smaller subcircuits in between, and it tries to optimize them using espresso. So espresso is used as a function which is called from MIS. Okay. This is roughly, I am not going into detail, but this is roughly the approach. This is used for local optimization, but for global optimization it uses a few techniques. It scans the whole network. It uses simple heuristics to clean up the netlist, like two NOT gates in series gets eliminated. This is called cleaning up. There is something called constant propagation. Constant propagation means if we have a gate with A and a constant 1 in the output feeding another gate, say an OR gate B, then you replace this entire thing by A. So this is equivalent to the simple OR gate A and B. This is called constant propagation. This constant propagates the value of A here directly. So this gate is eliminated. Double invert elimination I already mentioned, and each equation which you get for the subcircuits you use espresso for further optimization, because espresso is known to work well there. Okay. So after doing this you proceed to global optimization by using factoring and other thing, which is similar to Socrates. So this is also an iterative approach. So you just eliminate the common factors, identify the basic candidates, etc. So equations themselves may be common factors. Sometimes it helps in inverting equation. Say you have an equation like f equal to a or b or c, and somehow you are unable to find out any sub-expression. Suppose there is another function g which is a bar, b bar, f, but apparently there are no sub-expressions. Okay, but suppose you invert this equation f dashed, then this becomes a dash, b dash, c dash, and immediately this sub-expression gets exposed. So sometimes inverting an equation may expose further factors or sub-expressions. And again, since we are using CMOS as the target, number of literals is used to estimate the total area, right? Okay. So let us look at some of the examples, it will be clear that how it works. What we are trying to say is that in the global optimization step we are using factoring. Factoring means that weak division. We are trying to find out the common sub-expression and we are doing factoring. Suppose you have, or means you can also do factoring sub-expression together, because there are two things. One is common sub-expressions, other is factoring. Both will give benefit, as we will see through examples. So, our ultimate target is to do some kind of global optimization technique which can lead to a reduction in area. Now, an equation may be given in simple sum of products form. It will have literals, and it said that from the literals you can immediately count the number of transistors for CMOS realization. And our idea is that by identifying either common sub expressions or through factoring, we want to reduce the number of literals, and if we can reduce the number of literals, we can immediately reduce the number of transistors in the CMOS realization also. Now, let us try to look at some examples and see that how it can be done or how this is achieved. Let us take a simple example. Well, since it is CMOS realization, only negative gates, I assume that it is complement. I want to implement this function AB or AC. Now, naturally you can do factorization, and you can see that through factorization, in the first case the number of literals were 4, 1, 2, 3, 4, and here this has been reduced to 3. So, apparently we can expect less number of you can say transistors in CMOS realization. Now, in a CMOS network there is a pull up network comprising of p type transistors, there is a pull down network comprising of n type transistors. This is connected to VDD, this is connected to ground, pull up and pull down are connected, and this is the output. Now, pull up and pull down network are complementary of each other. So, if we just show one of them, other will be simply complement of that, and number of transistors out here is equal to the number of transistors out here. So, for this function, for example, if I had this AB or AC, okay, then the pull down network would look like this. A, B, A, C, 4 transistors. This sometimes we draw pictorially like this, just for convenience, instead of drawing the transistors, just to show like this. A, B, A, C. These dots represent transistors. Okay. So, instead of drawing this, we will be drawing it like this. And if we now do a factoring, this A, B or C, you can immediately see that our drawing, this picture now becomes like this. This is A, B, C. So, instead of 4, there are 3 transistors in the pull down. So, in the pull up also there will be 3 transistors, we are saving 2. Okay. So, number one thing is that if you are able to do factoring, then invariably you are reducing the number of literals and hence the number of transistors. So, this is one thing you have to keep in mind. Let us take another example. This is a slightly more complex example. Suppose you have a function like this, f equal to a b e prime f or a b g or a c e prime f or a c g or a d e prime f or a c d g. Suppose you have a function like this. You count the number of literals, you see that there are 22, 4, 7, 11, 14, 18, 22. So, there are 22 literals. Now, if we want to have a straight away implementation of this function, then with respect to the pull down network, there will be one arm with 4 transistors, 1, 2, 3, 4. There will be another with 3, 1, 2, 3. There will be another with 4, 1, 2, 3, 4. Another with 3, 1, 2, 3, and another 2 with 4 each. 1, 2, 3, 4, and 1, 2, 3, 4. Okay. So as you can see, you need 22 transistors in the pull up, in the pull down as well as in the pull up. Now if you just algebraically manipulate this equation, you can see that it can be factorized. This equation you can factorize, and I am showing you the final form. You can get it factorized into this. This is the final form. And here if you count the number of literals, you have 1, 2, 3, 4, 5, 6, 7, 8, only 9 literals. Now in terms of the implementation, you have gone down from 44 transistors to 18 transistors, and this is a significant saving. Okay. So simply factoring the equations alone will lead to a great saving in terms of the number of transistors. Well, not only that, you can also use common sub expressions. Like let us take another example. This example will highlight use of common sub expressions. Suppose I have a function f equal to abc bar plus adg plus ac bar f. There is another function g ac bar d plus adf. Now here again, if you follow the method which was used by Socrates, something similar to that, you will see that there are common sub expressions. One common sub expression you can identify is AC bar. AC bar occurs here, here and here. It occurs in 3 places. There is another sub expression AD. AD, AD, AD. AD also occurs in 3 places. So you can use any one of them. Okay. Now suppose we decide to use AC bar. So our modified equation will be U equal to AC bar, F will become UB or ADG plus UF, G will become UD plus ADF. If you count the number of literals now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Here 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you get one reduction. There was 15, it has gone down to 14. So you see that for common sub expression, the gain may not be as significant as factoring. So factoring is something which you should always try to do when your target is a CMOS realization. So even after doing this, you will be doing a further transformation using factoring. So U will be AC prime. For F, you see that you have a common sub expression U. So you take U common, B plus F or ADG. Similarly here you have D common in G. You take D out, U or AF. So here the number of literals has come down to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So from 15 you could bring it down to 12. So in terms of the implementation again, in terms of the implementation, again from here, from 30 transistors you have gone down to 24 transistors. So, essentially whatever this mesh does is based on transformations like this. Now in the method of espresso, there also the number of literals were used to estimate the cost of implementation, but in espresso the target technology was not necessarily CMOS. That is why there was some inaccuracy in the estimate of the hardware required, because they were concentrating only on the gate level netlist. I do a minimization optimization, I get a gate level netlist. But here, since our target is well defined, we are looking for CMOS implementations. So, we have a very fair estimate of the number of transistors, number of literals, twice of that is equal to the number of transistors. Okay. So, that is one thing. Now, in the optimization, whatever we have talked about so far, we have primarily looked at the problem of area. Delay is related, area we are minimizing number of transistors, okay, minimum number of transistors. Now, if our objective were to minimize delay, then we would have followed a different approach. The number of levels would be reduced. See, this implies that we will not do any division, no division, because whenever you do division, you are actually adding one level of logic, right. If you look at the previous example, whenever you did this division, you have to compute this u and output of the u has to go to here, okay. So, there is another level of logic you are adding. So, if delay is of more importance, then you should not use division, you use only factorization. But when your greater concern is power, of course, power optimization cannot be assessed so easily. So, there somehow we will have to measure or estimate the amount of signal activity in the circuit. The idea is that in a CMOS gate, if the inputs do not change state, the output obviously is also not changing state, and the quiescent power consumption of the gate is almost close to 0. But whenever the circuit switches, means the output goes from 0 to 1, momentarily the pull up and pull down networks both are turned on. So, there is a quiescent current flowing during switching. So, the switching current of CMOS can become quite significant, particularly when it is run at a high frequency. So, when you are targeting power optimization, we have to ensure that the amount of switching in the circuits is reduced as far as possible. There are ways to achieve this, but actually they are slightly beyond the scope of this class. There are ways to estimate the signal transition activity in a circuit, ways to control them by using control inputs, by adding additional gates. You can reduce the amount of signal transition activities in a circuit. Okay. So, today we had looked at some of the basic problems of multi-level logic optimization, and we had tried to get a feel that how this multi-level logic optimization tools work. There are some other approaches which is also used in practice for the purpose of representation as well as manipulation and synthesis of Boolean functions. In the next class we will be looking at one such method. It is based on something called BDDs, binary decision diagrams. That is a very efficient data structure to represent a function, and we will show that using BDD we can even carry out synthesis. We can synthesize a circuit, we can obtain some kind of a netlist starting from a given Boolean specification, and subsequent that would be talking or looking at the problem of high level synthesis, where from a given higher level description we can arrive at a register transfer level netlist, but that discussion we shall start from our next lecture. Thank you.